So let's think about how we can maximize this function quality of C, and I'm going to describe a couple of methods to do this. The first one is a useful thought experiment. It's on this slide. It's too inefficient, but we'll see with some modifications we can actually make it efficient. And it's basically a kind of greedy bottom-up approach. So I start off with every word in its own cluster. So I might have V and A, dog and cat, red and blue. And our aim is going to find, say, k final clusters. Maybe, for example, we might find k is equal to 3. And in that case, we do the following. So we're going to run a series of what are called merge steps. And it's really a very simple idea. Each time, so we start off with this partition here, I can consider all possible pairs of merges. So I could consider merging V and A into a single cluster, or V and dog, or V and cat, V and red, V and blue, or A and dog, A and cat, A and red, A and blue. So I can consider all possible pairwise merges. And so, for example, say I choose to merge V and A, then I end up with a new partition, which is that CV equals C of A is equal to 1, say, C of dog is equal to 2, C of cat is equal to 3, and so on and so on. So every word is still in its own cluster except for these two words, which are now in a single cluster. Now each time I consider a potential merge step, I form a new clustering, capital C, and I can calculate the quality for that clustering under the criterion I showed you on the previous slide. So I'm basically going to consider all possible merge steps like this and find the merge step which maximizes the quality of the resulting clustering. So say, in this case, maybe I would find that the and there is actually going to be the merge step that maximizes the value for quality of C. So that's the first merge. I now go to a second merge step, having merged these two words into a single cluster. And now I do exactly the same thing as before. I consider all pairwise merges, but now I treat this cluster as a single unit. So I could choose to merge these two words with dog, or these two words with cat, or these two words with red, or these two words with blue. Or I could choose to merge dog and cat, or I could choose to merge dog and red, and so on and so on. So again, we're going to do all pairwise comparisons where we just have one fewer elements now because these two words are considered as a unit. Let's say for the sake of argument we choose to merge these two. And then in the third step I might do something similar. Maybe I find these two words are merged. And I keep doing this until I end up with my target number of clusters. Say we have k equals 3 clusters in this case. So that's a kind of heuristic, greedy method where at each step I pick the merge step that maximizes this measure of quality. Naively, this is going to be very expensive. It's actually, you can show that it would take order the vocabulary size to the power of 5. But the IBM folks, the Brown et al. Paper gives a slightly more efficient algorithm, which is cubic in the vocabulary. That's an improvement for sure, but actually still too slow for realistic values of V. So again, this first algorithm is a thought experiment, and we'll see that the second algorithm I give you is much more practical, but this thought experiment was useful in that we'll use this basic kind of greedy bottom-up method as the basis for our algorithm. Okay, so this is actually the algorithm that people run in practice. And it has an additional parameter of the approach called m. The typical value will be m equals 1,000. Another property of this algorithm is we'll see that rather than producing just a partition or a clustering into k classes, it'll actually produce a hierarchy. So we might have something like red, blue, dog, cat, in a hierarchical clustering in exactly the same way I showed you earlier in this lecture. So here's how it works. We initially take the top m most frequent words. For example, the top 1,000 most frequent words, and we put each of those words into their own cluster. So we might initially start off with, say, the, a, cat, dog, and so on, listing the top 1,000 most frequent words in our corpus. And this is sort of the seed. This is the starting point of the algorithm. And then I iterate over the remaining words. So I go from the 1,001th word right the way through to the very last word in my corpus. And I'm going to consider each of those words in turn. So maybe the 1,001th word is the word sheep, for example. Okay. So I've added this, I have 1,000 words here. And I've added the 1,001st most frequent word here. And now I'm going to again consider all possible merge steps. So I'm going to consider merging the with a, or the with cat, or the with dog, right up to the with sheep. I'm going to consider merging a with cat, a with dog, right the way up to a with sheep, and so on and so on. So again, I'm going to do this all pairwise comparison, where I look at all pairs of words and choose to do a merge. So that would result in two of these words being merged. Let's just say, for the sake of argument, that we choose to merge cat and dog in this case. And so even though the sheep was chosen as the 1,001st word, it's important to realize that it won't necessarily be part of the merge step. I may choose to merge some other pair of words within this initial 1,000. Okay, so that's the first merge step. Now I add word 1,002. So maybe it's the word there, I don't know, something like this. And notice again, I have 1,000, I had 1,000 examples here, so after this merge step I had 999. So basically I have 1,001 different clusters here, where a cluster might be a single word or it might be a pair of words like cat and dog. And again, I consider all pairwise merges. So maybe, for example, I would take sheep and merge it with cat and dog in this case. And again, that's going to reduce the number of clusters I have by 1. I then go again. I go to the next most frequent word. Maybe this is red. This is the 1,003rd most frequent word. And again, I'm going to consider all possible pairs of merges, all possible ways of merging either a single word or an entire cluster with another single word or another entire cluster. All the way through this process, I'm using the quality criterion that I showed you earlier as a kind of oracle, which, given a clustering, will evaluate the quality of that clustering. And I'm picking these merges to maximize that measure of quality. Once I've added all of the words in the vocabulary, you basically have a clustering into, you can show you have 1,000 different separate clusters. And the last thing we do is carry out m-1 final merges, for example 999 final merge steps, and the result is going to be a full hierarchy over the entire set of words in our vocabulary. And this is exactly the process that the Brown et al. Researchers used, and exactly the process that resulted in those bit string representations I showed you earlier in the slides. The running time is the following. You can show it's the vocabulary size times m squared, where m is this value, say 1,000, plus a linear term in the size of the corpus. So while still expensive, this is nevertheless feasible for quite large corpora of training examples. And indeed, this algorithm has been applied to very large training corpora.